exactly derived the same way. In fact,
So you have to
coaxial mean, by definition. They share the same axis, which means they have the same center. That's actually important. That's why I'm mentioning it right now.
Did you say that they share the same center?
Okay. They share the same center. That's fair. Okay. A wire of radius A along that. Right. Wire of radius A, current going through it. And then a thin cylindrical shell of radius B. The current is directed into the page here. And it's directed into the page in the center wire that returns out along the outer axis. Dot, 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 dot. With me so far? It has 5 amps. 5 amps, and this distance here is 0.5 centimeters, which we'd immediately change into meters, right?
Yes.
And then B is 1.5 meters, which is 0.015. It should be. I just messed that up. Is that okay? Then it says calculate magnetic field at A, a point P1 in between the two, right? Then B, P2, which is outside the wire. All right, so let's do the one here. What's the shape I'm going to draw? 1 centimeter from the edge. I'm going to draw myself a circle. For Ampere's law, it's always a circle. Always going to be a circle. Now, I can technically start this thing off the way I'm supposed to. These things mean the same thing they meant before. It has to be completely enclosed. It has to completely suck up all the shape. It has to be symmetric so I can do the math. All that stuff is still true. Thank you, sir. He isn't in here. Thank you. Mu naught I. Okay. So that's B times 2 pi R equals mu naught I. B equals 2 times 10 to the negative 7th I over the radius, which in this case is 0.01. Now, the only question we have to ask is, how much current do I have going through that wire? Inside of the loop I drew. Okay. How much current is traveling through this loop that we just drew?
Is it just 5?
5. 5 amps are going this way, right? So 5 amps are going. There's a 5 goes right here. Slap it all together. 1 times, so I get 1 times 10 or 2 times something. No?
2 times 10 to the negative 5. Wrong, I think.
1 times 10 to the negative 5, so that would be 1, so it'd be negative 6. I'm getting negative 4.
Yeah, I'm getting negative 4.
I got 4.
Oh, yeah, 10 to the negative 4.
1 times 10 to the negative 4 Teslas, because that's what we measure magnetism at.
Negative field radius, not, because this is where Paul and I disagree with the radius, not be from the surface of the thing to the.
It'd be from the center. The shape you draw that determines the shape.
Shut up.
Ow. Is that a state school person telling somebody else to go to the University of Arizona? Oh, that's interesting.
No, they doesn't.
They make better telescopes. Huh?
Yeah, literally the only reason you go to U of A is to like become like some sort of doctor or something, or to study the stars. Nobody wants to go out of education.
Wow, you guys are harsh.
On Jacob, yes, we're harsh.
Yeah, what do you
I don't want to get into this because I'm about to say something unfortunate. Let's move on!
You can say it after class, it's fine.
You see your line
No.
and innovation.
Yeah, we teach real stuff. I'm going to draw my shape. Miss Perot on the outside.
Yeah. I'm guessing it's going to be circle.
It's going to be a circle. Every time it's going to be a circle. Now the question is, Miss Perot, how much current, if 5 amps is going through this middle wire, and 5 amps is coming in this outer shell thing coming back at me, how much current is coming, how much current do I have?
Is it 0?
That's 0.
0?
5 this way, 5 that way, I got 0.
That's what I like to hear.
Net current's going to be 0. So I'm going to get B equals 2 times 10 to the negative 7 times 0 all over 0.02, I think. And I get 0 Teslas.
So is this something called the cortex?
Where is me?
Matt, this is it.
There's a guy named Tesla.
No.
He was crazy and did bad
He
things,
does
and
not
they
exist.
decided to name a car company after him.
He does not exist, right? He was the worst Edison.
Actually, there's people that believe he's a conspiracy theory, that he's actually a person who does not exist. I have trouble with that particular magnetic field in any way, shape, or form. Let's say I've got it coming out at my forehead right now.
Looks like you.
Yeah. Okay, so magnetic field is coming out of the board. If I decrease the magnetic field, what's going to happen? If I decrease the magnetic field, what's going to happen to this wire? All right, lasagna, the first one that said something snippety. Lasagna are resisting change. If I don't want it to change and the magnetic field is going down, what must I do? Put current to make it go up. Now, first of all, why would current in this loop make the magnetic field go up? Right? It's just, we're back to B equals mu naught I over 2 pi r, right?
But how did you out those
Yeah,
inside
what are you
and
going
outside?
That's the part that gets interesting. We're going to talk about it in just a moment. But initially, the current to resist the change in here, I'm going to make a magnetic field, right? Okay? That's three supports all the way around the outside. Okay? Now, that current traveling in the wire, in this case, would have to go this way, agreed? Because that's what would make it go the proper way to support outside the loop. Now, Mr. Larson has an incredibly powerful objection. I want you to make sure everybody's got the first idea before he messes your brain up permanently. Okay. In order to resist the change, as this field starts to reduce itself down, the wire will go, oh, I just will start running this way. Let's start running this way to keep the field the same.
So now that's out.
Well, if it was increasing coming out of the board, then I would want less. I want to stop the change, wouldn't I? So then if I'm going around my loop, I'd have to go the other way, right? So if I'm on this side, it's stronger this way. If I'm on this side, going this way, this is in the board, right? In the board, in the board, in the board. If I'm going this way, it's out of the board, out of the board, out of the board, out of the board. Okay? Now, has everybody got that idea? What's happening there? This Larson's about to ask the worst question possible. Go, Larson!
Why is it out on both sides of the wire when it's supposed to be a split circle?
Oh, maybe I'm wrong. It would be, so that's the outside field I'm talking about, right? I'm talking about a field caused by something else, not by the wires themselves. Okay, good. So he didn't ask the question that I can defray for later, the actual question I was afraid he was going to ask.
Yeah.
Woo! Okay, good. So everybody got that? Okay, so if I want to resist change, how do I write voltage is caused by resisting change? Okay, so now I'm going to make sure I've got it written down right, because sometimes I write this down badly. I can feel it. I can feel it about to happen badly. Oh, wait. Oh, yeah, that's it right there. That's a lovely one. I don't like that at all. Yeah. Okay, so here's where we're going to write it. So, here is how your AP Central choose to write this. Are you ready?
They're listening.
They say the magnetic field, well, this is why they hate me and write different problems, just because of that. Sorry about that. The magnetic flux, the number of lines. The number of flux lines traveling through my loop. Don't panic, this is going to get so much better in about 5 seconds. I just need to get to it. Integral B dot dA. Okay, so the magnetic field permeating the space, same thing as electric field, same argument. The number of flux lines Is your magnetic field times the area is the total number of flux lines you have. We're never going to use this definition. They hardly even ever ask about it. Now, here's how IP Central wants you to think about it. My voltage is being caused by a change in the flux. If you reduce the magnetic field, you reduce the area of the magnetic field.
No.
If you reduce the area of the loop, you would create voltage. So voltage is equal to DIM dt. So these are the two formulas you write at the very top of your worksheet, and then I'm going to tell you what it really means.
Is M another variable? You just need flux magnetic.
It means magnetic flux rather than electric flux. Okay? Now, occasionally this pops up as something useful if you're doing something you're like, I'm trying to turn magnetic flux into electric flux or something weird. Occasionally this notation is not the worst. Generally speaking, you're never going to see it on a test. But there's some of the practice tests we can play with later.
Wait, so the ways you can make potential is...
Now, hold on. Here's what we're talking about. Because we're not going to do this. Here's what we're going to do. We're going to go V equals the change with respect to time of what? What do I care about?
Current.
The magnetic field's what's causing this. B, man. You change B, I'm going to have voltage. You change area. If I shrink this loop, I'm losing flux lines. That's going to change it. And last but not least, but not horrifyingly off task, is cosine theta. What if I turn my loop in a magnetic field? That's how we make electricity, isn't it? Turning loops inside of magnetic fields. Okay? This is it. This is the king. This is the one you need. Now, this formula is always going to break down to one of three choices. What are the three choices? V equals A cosine theta dB dt. Or, because you're changing the magnetic field. Or, V equals cosine theta B dA dt. Or, V equals BA d dt cosine theta. Okay? Those are the three ways you can make voltage with wires. Now, some of you are probably thinking, and wisely so, how the heck are you changing the area of a loop? Probably if I asked you to turn to a third free response question in any of those packets I gave you, you're going to see something stupid like this. Actually, not stupid. I like this problem. I shouldn't say that. I like it. I've got a bar. I've got a magnetic field. I've got a resistor. And what am I doing with the bar? I'm moving it. So what happens? The area is shrinking of my loop. Roger that. All
Let's
right.
run some practice, boys.
Let's do some practice. On the back, you have some practice problems to do. A planar loop of wire length consisting of a single turn of cross-section of 100 centimeters squared is perpendicular to the magnetic field and increases uniformly in magnitude from 0.5 Tesla to 2.5 Tesla. Please remind me, what does uniformly mean, Mr. Wolf?
The second derivative is just in a straight line.
Right. So you're talking about. Oh, that's really technical. So we're talking about a line, right? We're talking about a line. We're talking about if it's uniform, it means it's increasing in length. It's got a slope that's flat. Right? All right, try problem number 1. While I pause